Welcome to a new episode from the Energy Bridge. Today we are inside TU Wien to interview one of our professors in the Master of Science in Renewable Energy, Mr. Michael Harasek. Thank you for accepting the invitation. Today we're going to explore thermal energy, and it's something that we are trying to foster, that in energy transition we are only 23% electrified and the rest is heat. So what to do with it? And you have a really interesting projects going on, so we're going to go into it.
It's my great pleasure to talk a little bit more about it. Yes, so maybe my background. I did a study here at TU Wien of technical chemistry. And after my master's degree, I continued with my PhD at the Institute of Chemical and Environmental Engineering then. Here my topic was separations. What is sometimes misunderstood is that my field here is in German. It's called thermische Verfahrenstechnik. It has to do with heat. It has to do a lot with energy, but it has also to do a lot with substances. So one of my research focuses has been since then separations engineering. And separations on a molecular basis are exciting. So that means actually splitting mixtures. We all know about distillation, getting ethanol from a mix with water. We all know that distillation is done in refineries, in the classical fossil refineries, where we have this technology quite well developed to get our gasoline, to get kerosene, to get all the fractions, including very light and very heavy fractions here. This is all separations engineering. And as such, this field is, of course, also wider now, because the conventional technologies are very much related to high energy demand. So here, improving processes, using novel technologies like membranes and similar to reduce the energy impact and the energy consumption, specific energy consumption for a separation problem. This is one of those points.
So you are mentioning something that could be used in energy efficiency, but also carbon capture, for example.
Yes, carbon capture is a very interesting and upcoming technology, as you mentioned. But before, I want to give another example of a very energy intensive topic, and that is seawater desalination. Now we have to challenge the sweetwater supply, freshwater supply. Drinking water supply has become a major issue that also develops into big conflicts worldwide. We hear that. Rivers, the water of rivers is used in another country, and then the other country suffers from not having the water access, etc. So therefore, alternative aquifers like the sea and also brackish water, salted water, salinated water as a water resource has become more interesting. And here, new technologies, not distillation, that costs a lot of energy to evaporate the water and condense it again, but membrane-based technology like seawater reverse osmosis, for instance, is
what are the current
technology
being used in a lot in Israel and UAE and other
mixed. Thermal and also reverse osmosis. So and other membrane technologies. And we as separations engineers, now coming back to my original introduction, we try very hard to develop innovative and alternative solutions with low energy impact, less thermal energy demand, to reach the same separation purpose. But just let me introduce me shortly further. I did my career here at TU Wien. After my PhD here, I got a position here to continue my research and my activities, founding my own research group. Luckily, I had this opportunity here.
What is it about? Or
the original topic was on computational fluid dynamics, actually, and fluid flow.
Okay.
Because there's an old Latin word that says everything flows, pantare. Yeah? So that means in chemistry, in chemical engineering, in energy technology, we always are in contact with fluids. So that means knowing about fluid flow, knowing about mixing of fluids, separation of fluids, pumping, transportation of fluids is
Big topic.
a very hot topic. And so as a chemical engineer, I thought, well, why not jump into this topic and then proceed further? So I founded my research group, which was called Computational Fluid Dynamics then. It's still the same name, but we do lots of things now. But originally, we started very much into computation of fluid flow to understand the behavior in chemical processes, in reactors, in pipelines, in separation units, wherever we have the need to look inside without having the chance to look inside. And that is wherever it's very hot, where it's closed. We cannot look into hot processes, so we can only model it and then get a better understanding and extrapolate our findings and apply it to the improvement of an industrial process. And with this, actually, I advanced also with a research team that I could found from projects in the last decades.
Yeah. How was this approach to energy?
And my approach, my first approach to energy was again a material-driven one. That was to look at renewable methane, biomethane, more specifically. And as you may know, biomethane can be produced from biogas, and biogas can be produced.
That you gave us.
You remember that? So that means we have here a fermentation process, usually a digestion process, anaerobic digestion of various feedstocks, of wastes also, and they can be converted actually by the microorganisms to methane and CO2. And but this methane CO2 mixture, which is called biogas, is not ready for a substitute for the natural gas. But if you separate it, upgrade it, split it into the pure methane and the pure CO2, then it could be interesting. And again, this is a separation problem, a gas separation problem. And so that was my first, very closely energy related project that I did. And I was happy to be a project manager of such a facility, pilot facility at a capacity of 1 megawatt. It's quite something on renewables, 1 megawatt.
Back in the time, like in the
20 years ago. It was in 20. That was in 20
Pioneers.
in 2006. And here I was project manager of that project to inject the biomethane for the first time in Austria into the gas grid as a substitute. That was exciting because
What project was that?
That project was originally called VLTLS Biogas, and it was together with Energiepark Bruck and with Biogas Bruck an der Leitha in south of Vienna. It's like 40 kilometers southeast of Vienna. There is still a big biogas plant, and then when we started this project, all of the energy, all of the biogas was actually converted to electricity in gas engines. But we have to understand that a gas engine shows quite a low electrical efficiency. Usually it's 35, 38, up to 40 maybe. The best ones maybe 41, 42%. So which means there's a lot of off-heat. And in a decentralized environment, like in a rural biogas plant that is away from villages, the utilization of the heat as a byproduct from the gas engine is very difficult. Yes, there were also then projects to feed this heat into a district heating grid, a small grid, which is a good option. But there's the summer-winter situation. So
also, it's not used here as a fuel, but like in India and other South Asian countries.
Yeah, you can cook with it directly also with biogas. I know this. This is.
As compressed natural gas.
Yes, of course. Yeah, that is also for mobility purposes and as a fuel supply. That's an option too. Bio CNG, you can also do it for biomethane. Here the idea was to feed it into the gas grid and then substitute natural gas. And we know today that was at times when the natural gas was very cheap, and it was mostly imported from Russia. Some domestic production was there too. Yeah, and so everyone said, okay, biomethane is more expensive. Yeah, Okay, yes.
And
Now we are 20 years later. We were quite visionary with what we did then in this regard, and now we see that everyone wants to have biomethane as a substitute because it's green. It is produced from waste. We have quite a very feasible integration. Also, the times when the biogas was produced from energy crops is gone. Yeah? So now we have this good focus on waste, and also the regulatory framework is better. But that was my first touch with coming back to the original story line. That was my first touch into and getting in contact with the energy business, with energy supply systems, with grids, with operators that do gas supply, etc. And that moved onwards. We had then a couple of projects here where I was also partnering, looking at chemical heat storage, chemical energy, thermochemical energy storage. So to utilize chemical reactions to store heat and then receive the heat again with a reverse reaction. So that means you have a reaction of A with B to C, and then when you split C, you can get A and B again, and recover heat or store heat, whatever the A, B, and C the components are. And this is still an emerging field. We see there are some challenges still to be considered. And the other energy topic that I focused very much on and still focus very much on is hydrogen, green hydrogen in particular, because green hydrogen offers also the chance to decarbonize. So that means also reduce CO2 emissions of processes.
Especially the hard to abate sectors.
Fully agree with you. I think some say, there is a saying that green hydrogen is kind of a champagne. Yes, so and you wouldn't drink champagne on an everyday, every occasion basis. Yes, cheers. But rather use it efficiently because of its origin, because of its cleanliness, its quality, and also its potential. So to use hydrogen just to substitute natural gas for heating is probably not the best way, or use it in low temperature processes. But it's a chemical resource that we nowadays still produce at the rate of more than 90%, in some countries up to 99% from natural gas. Yeah? So by reforming.
That's blue?
No, that's gray hydrogen.
Gray hydrogen.
That's very gray.
Okay.
So we take fossil natural gas, and then just by using a catalytic reforming, we split it into carbon monoxide and hydrogen, and then transfer the carbon monoxide with water to even more hydrogen. But we release CO2 to the atmosphere. So all the carbon from the natural gas is released as CO2. And so therefore, this hydrogen is not green, it's gray. Yes. And to substitute also these hydrogen resources that's in the refining businesses, in the metallurgical industries, in high temperature industries, the glass industries, ceramics, etc., should be the first option and the first priority, utilizing hydrogen. And what it also means is green hydrogen is produced from fluctuating energy resources. So that means photovoltaics, wind, etc. And this requires actually also to manage a continuous hydrogen supply by combining the production with transportation and storage. These are some of my current research topic in the energy
that's amazing.
technology sector.
One thing that we want to compliment you about as well, that I'm sure that a lot more academia needs to interact more with the industry, and you're one of them who's constantly in touch with industry. But what do you say when people say that academic research, it stays in academia, it doesn't go to industry for implementation?
We can always look back and look into what my alma mater here has as a motto, and that is Technik für Menschen, technology for people. So it's our responsibility as researchers at the TU Wien, at the Technical University of Vienna, to develop technologies that have a chance at some point to be rolled out and can be applied to the benefit of the people. With this in mind, we cannot just move into our ivory towers, yes, far away from the world and from the people. We have to interact with the industry. We have to interact also. We have to look at socioeconomic effects. We have to do life cycle analysis with at an early stage with our ideas when we want to develop technologies for an industrial application. And so therefore, I think I'm one of those that definitely promote the interaction with the industry. That still requires, of course, also one aspect. I think research also should have a share of a budget and of resources for blue sky topics. So that means topics that are disruptive and that may never actually become a technology, but with a certain chance, because otherwise innovation is not possible. So it has to be a mix, working with the industry, solving everyday problems there, also implementing new technologies in the industrial sector, but at the same time also combine and be ready also for disruptive, crazy ideas and establish an environment at the university. And that's what I do with my team, with my research team, to say, okay, let's
try.
Let's try crazy things. Yes, and
Good. And in that regard, that university working with industry for people, you have a project about gas separation with some industry here in Austria, OMV, for example. How has been the experience working with one of the biggest refineries, working in gas separation, and which challenges can be in this topic, like working with the industry in this sector?
Taking the innovation from the research to the industry.
Yeah, no, this was our first hydrogen related project was called Highly Pure, and we did this with OMV. Then here the idea was to develop a blending and a deblending technology of hydrogen, so to utilize natural gas pipelines by adding hydrogen and removing it downstream somewhere. And this downstream removal and separation technology, we call it deblending. So after mixing, to separate this again, this was our target in the research. And or working with industrial partners, like big partners in general, is I think to develop a perception, of their needs, because the industry has different timelines, has different targets. So also here to offer outputs
to align, kind of,
to align the vision of the industry, the targets of the industry, the goals of why does the industrial sector you work with approach you at all or wants to develop a certain technology. This understanding and also the openness to understand this is, I think, a very important success factor or key success factor in such a cooperation. This doesn't mean that we as academics or as the academic sector sell our performance, our output directly to the industry, but doesn't mean that at all. I think in a good cooperation, and the one that you addressed here, with OMV, it was such that also some of the output or some of the research that we could do during this project was actually also strategic. And that even allowed us to develop at the end or after the end of the project further technologies that resulted in a patent prize and things like that. So that means also disruptive new ideas that came out of the original project. But we actually delivered what our partner wanted in such a cooperation.
So it was a success, and they were happy afterwards with the innovation.
I believe so, because we gave them in their hands the potential actually to apply the ideas. And also what's important is when you work with industries, always to look at aspects of the economics. So what does it cost in the end? How much is it? And if we talk about hydrogen and sweet hydrogen, what is the cost of such a deblending technology, for instance? So in the end, I think in such applied research environments, we have to look at that aspect as well, and make ourselves also ready, have a background, have a certain understanding, and also actually look at the numbers in this regard as well. Yeah.
One of the questions that we wanted to also ask you, how we go forward about success metrics of academia, maybe in the sense of patent that can be commercialized, or maybe CO2 captured, or any other creative manner, so that we know that it's going beyond papers.
Yeah. No, that's of course, there was there was always a saying, and still there, and it still has a certain truth, and that is publish or perish. If you want to be successful in academia, you have to publish.
Yeah.
And this developed into Hirsch factor, into number of citations, and in all this. But this is only a part of the truth, because nowadays we also see that this focus has actually turned some parts in academia into a publishing machine, more or less. A machine. It's the only thing that we have there, not so much considering quality aspects and really
Impact.
innovation and impact. Yes. So and as such, we have to be very careful looking at these numbers. It's also when we have job openings, and we get international applications, we look at the publications, yes, but also how much was done by the, let's say, a PhD student, postdoc who actually applies to an open position, other than just look at the numbers. So what was the project, and what was the impact of the project where he or she was in? I think that is equally important. Patents, of course, have become also a more important measure than ever, in particular at universities that are more in the technical fields and in the natural sciences field, because a patent itself has a chance actually also to generate licensing fees, and could be an entry point, an entry to a successful cooperation with an industrial partner. But at the same time also offers opportunities for spin-off startups, etc. And TU Wien, also with its current rectorate, has a clear policy to foster patents and to increase the number of hopefully successful spin-offs and startups. So that means here, I think it is also a management question of the respective university to support and form a climate and a support for innovations towards patents. So that means we as researchers, actually, we have to think before we publish whether the idea that we have and the news that we have and the novel data that we have might actually also be ready for patenting. And this mindset, we have to train also our young researchers that they cooperate in this direction further.
Yeah.
And we as mentors, as the old ones, we have also to see the potential with our experience.
Yeah, because we think that academia should be measured not only by papers, but only with all other metrics. So if we can help with that, more than happy. And now we wanted to ask you, were again from separation of fluids, in this case gases, thinking about Eastern Europe, that they still have coal-fired plants, how to use this technology, membrane cryogenic membrane, to separate carbon from these plants, to make retrofit or carbon capture, to kind of decarbonize, being part of the process.
Decarbonization of the industrial sector in sectors where, and in countries where there is 80-90% fossil energy supply, as you mentioned, coal is still in a couple of countries of the of Central and Eastern Europe is a relevant fuel that is used because it's available. It's maybe even domestically within the country available. So why not use it? Yes, and so therefore it is also a question: how can we actually reduce also the emission from fossil energy, fossil fuel consumption? Yes. Okay. And here are certain potentials, but of course we have to understand that also these are limited. So short time, it is possible, for instance, for coal, for instance, to collect the CO2, to separate the CO2, which this bundle of technologies that we have to date are called carbon capture technologies. So that means we have a combustion process, and then we try to collect the CO2 as pure as possible, maybe also liquefy it in a cryogenic way. So that means we make liquid CO2 and then we bring it to an underground storage, which is called carbon capture and sequestration.
Okay, so if we could go a bit deeper, how it works, like this membrane cryogenic. What is the...
So one of the options is, as you say, we can actually combine any kind of CO2 separation process that includes membranes as a first step. Could also be immal absorption. It could also be an adsorptive process to collect and increase the concentration of CO2 to a certain level. And then when this CO2 shall actually be brought into underground reservoirs that are ready for it, it requires very high quality of the CO2 with the target not to damage the storage site with the contamination. So that's also the reason why the CO2 that's actually collected from a flue gas, for instance, from a combustion process, should be quite clean. And so one of those second step is also to make it transportable, is with a lot of energy consumption again, is to liquefy the CO2. So that means we cool it down to very low temperatures and get the liquefaction. And then that also reduces the volume. And then we can use actually insulated tanks and also transport it by railway or so. This is a transition technology. That's very important. Everyone says, okay, yes, well, now we have the technology, but we have to consider that anything that we do to collect the CO2, to liquefy it, to transport it, to bring it into an underground reservoir is energy intensive. And it creates maybe also secondary emissions. Yeah. So as such, looking into the CEE countries, that may still suffer from a lot of fossil energy consumption. We in Austria, we also have still quite a high level of that, but we have a clear decarbonization and net zero strategy that was issued by our government, and as such, I think the only way to get out of this is to reduce the consumption of fossils, and this can only be done by substituting the fossils with renewables, hydropower, photovoltaics, wind. These are, and maybe biomass. Yes, okay, biomass is also to be considered here, and in particular, big countries that have a large biomass potentials. Why not also look at that? Yes, that is, I think, that's also interesting for us as chemical engineers because we look a lot in conversion technologies to utilize the biomass first on a material basis and then also harvest the energy. So also this is exciting. But other than that, this is the only way. For natural gas, there is also a reported technology that comes into discussion now, and that is pyrolysis. So that means methane, as you may know, is CH4. So it's carbon and hydrogen only. So what can be done is actually to split away the hydrogen and recover the carbon as pure carbon, as black carbon. And this is a technology that is at the moment at a certain level, TRL level, and it's being discussed. But it has to be noted that this is a transition technology as well, because we use still the fossil natural gas. Yes, we consume it, split it into carbon that can be that does not create a CO2 emission, which is right, and we harvest the hydrogen. The pyrolysis itself is an energy-demanding endothermic process, so it needs a lot of energy as well. So as such, the recovery of the energy from one molecule of methane is much less when we burn it in relation to when we just split it and recover the hydrogen as an energy source. So in the end, fossils have to be abandoned at some time.
Yeah.
And that must be the clear target also for CE countries.
Going forward, one of the debate that is you touched upon that hydrogen should be like champagne. And
it's currently champagne because it's expensive still.
And
it could be cheaper.
So the whole thing about electrification versus hydrogen, where you think the industry should prioritize the heat pumps and where they should have green hydrogen. We know that currently the industrial heat pump does not have the high temperature range, but still, I mean, just for the understanding of the community as well, like if you could tell us where is the difference lies between electrification and hydrogen, where they can be used separately for industrial processes.
Thank you for this very relevant question. Actually, well, heat pumps, as you may know, allow the increase of the exergy. So that means heating, increasing the temperature of a heat source. So a very good heat source is the environment. So in heat pumps, we can actually recover the heat from the environment, which is at low temperature, is at ambient, at 20 or 15 or even lower, in the winter even lower, and pump this and bring the temperature of that enthalpy to a higher level, to the output level. And that depends if it's a single stage or a two-stage heat pump, then this temperature difference between the in and the out can be higher. So we remove heat at low temperature level and provide heat at high temperature level. And for this pumping, we need electricity. And the ratio of the amount of heat, of energy that we pump in relation to the electricity input, what is called coefficient of performance. So the higher this value is, the better is the heat pump technology. And of course, the higher the spread is between low temperature and high temperature, also the more difficult it gets, and usually the COP, this coefficient of performance, gets lower. Heat pumps are for sure low temperature technologies. So that means when high temperature heat is required in a process, it can be provided either by electricity directly, but when we use ohmic heating, it's called ohmic heating. We just have the electrical current flowing, and that generates heat in a resistor. That's ohmic heating, and here the coefficient of performance is just 1. So it can never get higher. So here as such ohmic heating is for a certain high temperature application is an option. But also here we have limitations. These are material aspects. And for the very high temperatures, I mean these are temperatures above 1,000 degrees. We can only rely on combustion technologies or high temperature conversion technologies, and here hydrogen may come into place, where hydrogen is either burnt or reacted at very high temperature, and as such, for high temperature process, hydrogen could actually substitute what we use now, that is natural gas, for instance. Yes, and furthermore, also we have lots of other high temperature processes where the function of our fuel is not just for creating heat in the combustion, but also as a reactant. So for instance, in the production of steel, of iron and steel, methane reduces the iron ore to pure iron, to elemental iron. And this can be actually also be done by hydrogen. So hydrogen as a reducing agent, as a chemical agent. And so that's the reason why I consider the use of hydrogen in the industrial sector as that what is, use it as a champagne. So use it wherever we have very high temperature processes.
Yeah, just two things to add, that we went to your office and you had some thesis topic to be taken. And there is one which is maybe interesting for someone, which is hydrogen burners.
Yes.
That's a good one. And the other thing is since you have said that it's in higher temperatures, it's not possible to use heat pump, which will be a solution for electrifying the industry. It's we knew about a project from AIT, Austrian Institute of Technology, that they are researching about high temperature heat pumps
they do that,
in the pharmacy industry. So we're very pending or what's happening, what's the outcome of this project, because it's going to be released the results in September or October this year. Now we are in August.
Oh, okay.
So yeah, it's very relevant topic. And since we are in the AI era, which solutions do you see that AI could address in your field of research?
AI or most of the AI tools and techniques are not so new as we believe. Working with data, machine learning, artificial neural networks, they have been around for more than 20 years or even longer. We had fuzzy controllers. At some point, you can buy a camera that has a fuzzy focusing system or something like that, which is actually also algorithmic-wise AI, yes, because it uses data and then takes action, does something with it. And for us in chemical engineering and also in the energy technology, rethinking AI tools is something that is currently ongoing. The potential is huge, yeah? And that is combining data science, so the data of existing processes, the data that we create in the process control of our plants, of our equipments. Yes, this can be harvested actually, and also used for the sake of predicting certain phenomena, for extrapolating, improving process conditions, optimization, or also predictive maintenance, so that we see from the patterns of our data, we see a development that goes into, let's say, the failure of a piece of equipment. We have more vibrations, that we have a higher temperature, that we see something that there's all of a sudden there is a change, and that actually is something that we see. So using data-based tools, we call it AI, let's say, yes, as an everyday procedure in the data analysis of our existing plants, where we do the process control, the sensors, everything. That is something that is very interesting. But also, I think that we do a lot in chemical engineering with our computers. So we do modeling, we make process simulation, we do computational fluid dynamics. And these are still highly computational intensive, even higher computation intensive than AI tools, because they are also computationally extensive, and we hear about the energy consumption of AI, of large language models, etc. But here, combining our in silico methods, so the computational methods, with data scientific approaches, AI tools will actually speed up our computations and reduce the efforts. And here we are still at the beginning, bringing AI and the combination of AI with our data that we generate from models, from simulations, but also from experiments.
To make more simulations in less time.
Yes, or not to make any simulations at all anymore, but develop a model or an equation, or or lookup tables, or even also an AI-based information that we can generate without doing the simulations anymore. So we do a certain bunch of simulations and then put them into the database and let them be analyzed by our machine learning tool, whatever we use. Yes.
You've worked a lot with the biorefineries and circular economies. What do you think about agricultural residue being used as a supplement, or you replace it for the gas in food processing?
Using our resources properly, and renewable resources in particular, is a key success factor for the transition of the energy system. So that means these resources. What happens with waste? What happened with waste in the past? Yes, they were just let there, and they degraded slowly by microorganisms, contaminated maybe our soil or our water reservoirs, our aquifers. And if we do that in a controlled way in a biogas plant, we can harvest the nutrients in the liquid phase, and we can harvest the energy in the gas phase. And we can maybe even harvest water by applying separation technologies on the liquid. Yes. So with all this, we have a much better situation, because we can substitute, looking at the nutrients, we can substitute fossil-based fertilizer production. Yeah. Ammonia is still very fossil-based, because we still use a lot of natural gas for the production of hydrogen, for the production of ammonia. So if we in a circular economy, a circular bioeconomy regime, we should actually also recycle and loop our fertilizers, phosphorus, and a highly valued element now, or also potassium and the others. That can be done. So that means using waste, bio-waste, is for sure, if you do it right, is for sure a good solution, in particular for the rural environments.
Yeah, cool. And now maybe moving into policy-wise, do you see some barriers, or what should be enabled to have more deployment of carbon capture solutions, or more chemical solutions in energy sector? Have you seen some barrier in the policy?
There are barriers in the policy for sure. That's something that will always be there. But what is important for the rollout of renewable energy is a good policy framework at national basis, regional basis, but also a supranational basis. So in the European Union, for instance, which means that reducing the barriers, for instance, for hydrogen or for biomethane, we have some directives to have non-discriminatory access for renewables. Yes, but still, it may be a problem actually for a renewable energy producer to get access to the grids, to the whether it's a gas grid or whether it's an electricity grid. So here we see barriers. I also see barriers, of course, in the market, in a renewable energy market, in a biomethane market, or in the development of a hydrogen market. And here there are, I think, good approaches now with the European Hydrogen Bank, actually also to stimulate a market. Because if there's a market, if there's demand, then this is a driver actually also for the investment into renewables, in the production of the electricity and in the conversion to hydrogen with electrolyzer technologies. And so these are all instruments actually that reduce the barriers and allow actually also the rollout here. But barriers we also see, for instance, a lot in the installation of electricity via photovoltaics or wind. You cannot just get or combine agri-photovoltaics, for instance, as I think a high potential approach to combine agricultural use of land with the production of electricity, and at the same time may even have an advantage on the water, on the water consumption because of shading, etc., and on the growth of fruits or agricultural products in a better way in very hot and dry regions. And still there are barriers actually because of the landscape, so we have to actually look at these aspects as well. Same with wind turbines. We see that there is a growing opinion in the public actually not to have any more. And this is a problem that I think that can only be solved mutually together with the people, but also with a good regulatory framework.
What do you think is happening now in terms of heat in Austria? In terms of, let's say, the other Eastern European countries, they're still reliant, and can Austria do some technology transfer, take the leadership role for those countries? help them?
Heat. We have to distinguish between heat for the industry and for the end users to provide hot water and the district heating in the houses and in the buildings. And looking at that, what we see in Austria is that in the more congested areas, like in the cities, meanwhile strongly developed district heating grid, so a hot water grid that supplies actually the end user. And this means also that we have a move out from natural gas utilization, having boilers, local boilers, but rather have a connection to this kind of grid. And in less congested areas, the heat pump is for sure an option. And I think also here Austria for some time had a very interesting funding regime, so that also to foster and support private people to just move out from their fossil heat production into a green heat production by either applying a photovoltaic system on the roof, electricity storage, or having heat pumps installed and not anymore an oil boiler system.
And also for industries?
Of course, here too, this what you mentioned already, the industrial heat pumps, the big heat pumps are for sure an interesting technology, but also a transition of the technologies that are applied. So that means actually the amount of heat that the production of a unit piece of a product requires can be reduced. So that means also the industry, I think, is aware. The stakeholders and the decision makers are aware of the potential. What we need is an investment friendly environment that also supports decision to invest into low energy demanding technologies at all levels.
So speaking about investment, we have a question now that it's what would you fix in energy sector with 100 million euros to accelerate energy transition?
I'm still from academia, and what we still need is investment into innovative solutions. So that means for sure a big share of that money I would definitely invest into applied research. So R&D activities, having pilot labs, having and allowing also to have an overcome of what we call the valley of death. As you know, when you develop a technology, it's good in the lab. You start with an idea that's TRL1 and then moving to the first proof of concept and so on. And at some point, it gets expensive. It requires a lot of money actually to overcome it and to make a technology, to bring it to the rim of commercialization. And that means also to attract investors that want to see it at a certain scale. And for this is exactly where I would use this money. Okay. Yes, and in a couple of ideas that we have to screen, including also hydrogen technologies, of course, which is my topic. Yes, but then to allow this for scaling, and to overcome this value of debt.
So, which project would be that you finance first?
My own one, my current one. That's my electrochemical hydrogen separator and compressor. That's a new technology that allows hydrogen compression without any moving parts, and includes a separation.
Not in moving parts.
Yes, there's no piston, no rotating something.
So how you increase the pressure?
We increase the pressure by just transforming, by moving the hydrogen from one side to the other side of a membrane. So we come back to what I talked about at the very beginning. I like membranes, and they have a great potential.
Also, 100 million for professor, please.
Yeah. One question just on membranes. We were reading somewhere that the MOF-based separation, it uses some material which is a critical mineral and comes from Chinese rare earth. And is it I mean, because critical mineral is such a political topic, is it still being used? What are your views on it? MOF based separation?
Yes, I know what I know what you mean. Just also for the audience, MOFs are so-called what we call metal organic frameworks. And this is a group of materials that have like a kind of almost crystalline character with certain polarities, and which allow actually the movement of small molecules into such materials. So that means bringing this to a membrane process or bringing this to a separation process, if we use this material, it will allow a certain molecule to move into that framework and pass through very quickly. So that can be used in separations of CO2. It can be used in hydrogen applications, storage applications, also separation applications. You're right. We have to be careful which materials to use and whether we use. We have another, let's say, demand for critical materials, critical raw materials. But there are, of course, strong ambitions also in research, and we also did it just with a recent application. Where we try either to abandon critical minerals and or substitute it in a good way. So that means this is something that we see, and where we as researchers have a certain responsibility. At an early stage when we develop a technology, we have to have a view of which materials do we need for that, and whether there is a chance to substitute them for less rare materials, cheaper materials with less environmental impact. And so as such, this has to be always in the back of our minds, even if the idea is great. But if it creates another problem, we have to be aware of, okay, shall we really follow this idea?
You currently, in terms of their supply chain of critical minerals, are they excessively reliant from other countries?
I'm not an expert in that field. But what I see is, and what I of course heavily observe is the discussion. Is also the political impact in getting national, international contracts to have a supply chain or safe supplies. What I see is for us as chemical engineers, and that's the exciting thing again, is to loop its use. So that means we have already quite a lot of critical materials here in any country on stock. Because we have used it for a time. And the end of its, when it comes to the end of life, to the end of its use, we have to develop improved and reliable recycling technology to recover the materials again. So also here, if we talk about photovoltaics recycling, if we talk about lithium battery recycling, if we talk about the recycling of magnets which contain rare earths, etc. So I believe that the further development and also investing, maybe one of those millions could be also invested in this regard, is to close the loop and develop a sustainable supply chain of such minerals by just using what we already have and what can be partly recycled. It's already well established in the iron and steel industry. 98% of the materials go back in the loop. But for lots of other stuff, it's not yet established because of costs and because of a lack of reliable technologies.
About resources to research, would you find one reform in European grants to research that could be improved?
We could have a discussion of an hour just on this topic.
Okay, wow.
But in short, I think we lose a lot of resources in academic resources by submitting project applications for grants with a success chance that is in the range of 2%. And if you look into some ERC related grants, into European grants that are disruptive, that are high level, we have a high competition. And the competition is for 2% chance. So that means 49 proposals fail and one proposal is successful. And so this means that 49 groups actually took a lot of effort, energy, costs, manpower, human power to actually submit this proposal. And so here we have to come to either a pre-selection process or actually just more money into that. And so this loss of resources in unsuccessful grant applications is something that has to be addressed in the future.
And how could it be?
As I said, pre-selection, overcoming frustration by all those that write the proposal and again get a reject. Yes, and also combine it with a better distribution of money that is available or increasing it. So that's the only way.
Could be another way of just helping them to spin off and then private money coming into it.
Public-private partnerships are great, yes, but you cannot apply this to any technology readiness level. So this is usually something that requires also a business case for the investor at some point. And that's only possible at higher TRLs. But at lower TRLs, and we have lots of fundamental researchers or researchers that do fundamental research, and in that field we definitely lack budgets. In Europe, in Austria in particular, also I see this, and this needs some guidance and some action actually to not waste time and money of unsuccessful applications.
So, well, time flies.
Time flies.
And we would like to know some advice from you to the new chemical professionals that are entering in energy field. Which advice would you give them?
Yeah, I'm a chemical engineer. And as chemical engineer, learn chemical engineering first. That's always a good advice. Chemical engineering is very much about balancing, material balancing, energy balancing, and a proper knowledge of thermodynamics. And in particular, when we look at new ideas, crazy ideas, we do have to challenge it also against these governing rules that we have, which we cannot. Physics is physics, so there's no way. So physics is also an important aspect. So having a good foundation here is important. Also to be professional. Chemical engineers are interdisciplinary by definition, because we are at the border of chemistry, mechanical engineering, electrical engineering, physics, biosciences, etc., depending on which field, and as such, learning the different languages to have a better understanding is important too. And those that become professional and target management, also more entrepreneurship, etc. So that means also this is an important aspect. Learning about this, how to be successful in this very competitive field, is also a good thing. Yes. So how could I become a good entrepreneur? And more chemical engineers as entrepreneurs would be good too. Yeah.
So, Professor, your last thoughts about the interview and our mission to bridge the academia together with with industry and policymakers.
As I have discussed before, it is very important to have that, so this requires readiness on both sides to do that. So the willingness actually to understand the problems of the industry and industrial sector, for us as more on the academic sector, and vice versa. This is a prerequisite, and then also we need channels and ways and means on how to foster it at an early stage to get and gain understanding by the industries, by the investors, for instance, of new technologies that arise. So getting excited about research, and also have a very positive image or improve the image of universities, of academia, of R&D in the society. That's super important. And here we see also with alternative news call it fake news or whatever, we see that there are alternative truths told that have no scientific foundations, and to act against this, I think, is one of our responsibilities, both on the professional and the academic sector.
Okay, good. I think it's good words to close this amazing interview. Thank you very much, Professor. Very insightful, and I hope that is insightful for the community too.
Learn chemistry.
Learn
Learn chemistry.
And yeah, thank you for watching the interview until the end, and see you in a next episode.
Thank you.
See you. Bye.
Bye-bye.